So we start now. So good afternoon and be welcome again to the online edition of the Astrobiology School at Observatório Nacional. So for the next lecture, we have a great pleasure to have here Dr. James Kasting. However, before we start, just some information again for you attending at the Astrobiology online. So after the presentation, there will be time for questions for people here at Zoom. For people at the YouTube, please write your questions in the chat. It can be in English or in Portuguese, and your questions will be read by us to the lecturers, okay? And second, and very important, we'll share in the Zoom and the YouTube chats a link for the attendance list for those who want or who need a certificate. So there is a different link for each lecture, and you just need to click on it, fill the form, and send it, okay? The list will be available up to 10 minutes after the end of each lecture. So please don't forget to include your name and your email, okay, in the list of each lecture. So let's come back for the lecture of this afternoon. So as I said, it's a great pleasure to have here Dr. James Kasting. Dr. Kasting is an American geoscientist and Evan Pugh Professor of Geoscience at the Penn State University in US. He's active in NASA's search for habitable extrasolar planets, and is considered a world leader in the field of planetary habitability, assessing habitable zones around stars. He was elected as a member of the National Academy of Science in 2018. He has been serving on the Venus panel of the ongoing Planetary Science Decadal Survey in the US, and continues to be interested in matters related to the long-term evolution of planetary atmospheres and climates. So for your lecture at the Astrobiology online today, he'll tell us about the search for life on planets around other stars. So thank you so much again, Dr. Kasting, for accepting our invitation. Please.
Okay, well, thank you, Marcelo, for inviting me and for your kind introduction. Thank you all for attending. I wish very much that I could be down there visiting Brazil, which I've never managed to visit, but maybe next year that will be possible. Let me share my screen here. Okay, everybody see that?
Yes.
So this is a topic that I've worked on and off for the past 30 or 40 years. And I want to start out by talking a little bit, give some background in general, because I find, when I've given this talk in many different venues, and I find that if I don't start out by talking about the requirements for life, then the rest of the talk doesn't make too much sense. So I'm going to, part one, I'll just list 4 basic requirements for life, which I will assume for this talk. Part 2, I'll talk about the habitable zone around stars, which is something that I've actually worked on myself because I'm a theoretician, and one of the things I do is run climate models. Part 3, I will mention some recent and not so recent developments in the search for habitable planets. And part 4 is what I'm really most interested in these days, which is how can we observe potentially habitable planets in the future. All right, well, let me give the first 3 requirements that as I see it, for life on this slide. First of all, you need a planet with a liquid or a solid surface. And that means no gas giant planets like Jupiter or Saturn or Uranus or Neptune. And why is that? Well, some people are more optimistic than I am about this. Carl Sagan, if you ever saw his film Cosmos, had pictures in there of these giant creatures that would float up and down in Jupiter's atmosphere and adjust their height in the atmosphere, much as some fish do adjust their depth in the ocean using air bladders. But such a creature would be highly evolved. Life forms, we think, as single-celled organisms, and they would be impossible to. It would be impossible for a single-celled organism to maintain its altitude. So I think you need a planet like the Earth or a water world, some planet where you have a phase boundary with stable pressure temperature conditions. Second, you need a thermodynamic free energy gradient to drive metabolism and growth. There are some original lifers think that that metabolism actually comes first and that life is a response to free energy gradients. I'm not going to focus on that too much today because I'm going to talk about surface life, and stellar radiation provides abundant free energy for life on the surface of Earth. So that's not really going to factor into my talk today. Third, you need availability of carbon and other bioessential elements, sometimes called schnapps. That's assuming that life is life as we know it. It's carbon-based. That's probably a safe assumption, and it's a useful assumption for the talk that I'll give today, which is focused on life on planets around other stars. Then finally, the last requirement that I will use today is the requirement for liquid water. And that one's more controversial. There are researchers who have suggested that life might, some alternative form of life might be able to do without it. But for instance, Saturn's moon Titan is covered with lakes of liquid methane. And some of my colleagues would actually like to go there and explore those lakes and see if there's anything living in them. But I'm going to talk about exoplanets today, and I think it would be very difficult for us to recognize life on a planet that didn't have liquid water like the Earth. So I'll focus on that. I'll also focus on surface liquid water. In our own solar system, there are several bodies that we're pretty sure have subsurface liquid water. Mars, for one, Jupiter's moon Europa and Saturn's moon Enceladus, we know have subsurface oceans. And that's very interesting to astrobiologists who are interested in solar system exploration. But here again, I'm focusing on exoplanets, which we're only going to be able to observe remotely unless we invent warp drive or something, which I don't think is going to happen soon. So then you want the water to be on the surface so you can have an active photosynthetic biosphere that can modify the planet's atmosphere in a way that we might detect remotely. So that leads to part 2 of the talk here, which is on the definition and boundaries of the habitable zone. I'll take the definition of the habitable zone from 2 papers by Michael Hart. Michael Hart was, back in the 1970s, Hart was a planetary science at NASA Goddard Research Center, and he defined the habitable zone as the region around a star in which an Earth-like planet could maintain liquid water on its surface at some instant in time. Hart also defined what he called the continuously habitable zone, or CHZ, as the region in which a planet could remain habitable for some specified time period. So if the habitable zone at some time T0, if you can see my pointer, went from here to here, then later the sun and other stars all brighten as they age on the main sequence and convert hydrogen into helium. So at some later time, the habitable zone T1, the habitable zone might have moved out to here. Then the overlap between those 2 zones is what Hart called the CHZ, or continuously habitable zone. The footnote over here on the left points out that the term habitable zone actually goes back much farther than that. I'm indebted to Ralph Lorenz for pointing out a couple years ago that Walter Maunder used that term in a 1913 book entitled "Are the Planets Inhabited?" Some of you may recognize Maunder's name. He's famous for what's called the Maunder minimum, which was a period in time around the year 1630 to 1700, I think it was, where a period of 70 years where sunspots seem to have disappeared on the sun. But he was also interested in habitable planets. All right, well, I read Michael Hart's papers while I was in graduate school at University of Michigan in the late 70s. And to me, they were very depressing because Hart was really a pessimist. I had grown up listening to Carl Sagan, and Sagan was very optimistic about the possibility of life elsewhere. Hart's model suggested that the 4.6 billion year continuously habitable zone around our sun is really quite narrow, that it went only from about 0.95 astronomical units on the inside, 1 AU, of course, is the average Earth sun distance, to about 1.01 astronomical units on the outside. You get runaway, in his model, the planet would experience a runaway greenhouse if it formed closer than 0.95 AU, and runaway glaciation if it formed farther from the sun than 1.01 AU. And then he did a second paper in 79 where he applied this same model to other types of stars, other spectral types. And his model, which he tuned specifically for the Earth, was even less successful in predicting habitable planets around other types of stars. So a corollary to his study really was that Earth might be the only habitable planet in the entire galaxy. And that if you look at old astronomy textbooks, there are a lot of pessimists out there, and some of them picked up on Michael Hart's calculations, and you can still see that included in older textbooks. Well, you know, I was, as I said, somewhat dismayed reading this as a graduate student, and I wondered at the time if there might be problems with that model. Well, I think there are, and you know, I've listed a few of them here. One is that his greenhouse effect was really not very strong. He used a parameterization of the CO2 greenhouse effect, which was actually very weak. And therefore, in his model, if a planet ever fully globally glaciated, it could never recover by building up CO2 in its atmosphere. Whereas our models today, I'm not really going to go into much detail on them, but we find that you can deglaciate a frozen planet. In fact, I'm in a geoscience department and we study climate history. Some of you may be familiar with the Snowball Earth episodes. There were two of them in the late Proterozoic around 600 or 700 million years ago, and probably a third, at least one more, back around 2.5 billion years ago at the time of the Great Oxidation event. So we think that the Earth actually did freeze over at least 3 times in its history, and it recovered from that. How did it recover? Well, the theory is that it recovered by building up CO2 in its atmosphere because of a negative feedback in the carbonate silicate cycle. So here's a cartoon of the carbonate silicate cycle. That term may be unfamiliar to some of you. Astronomers don't usually study these things. The carbonate silicate cycle is part of the carbon cycle. And the part of the carbon cycle that most people are more familiar with is called the organic carbon cycle. That cycle is, in one direction, it's photosynthesis. Plants take CO2 and water and turn those into organic matter and oxygen. And that's reversed by respiration, which is carried out by both plants and animals, in which oxygen reacts with organic matter to give you back CO2 and water vapor. There is an inorganic carbon cycle, though, too, that's just another name for the carbonate silicate cycle. And that's what's shown on this slide here. I neglected to mention the organic carbon cycle is fast. It's very important in the climate system and other parts of the Earth today, but it really regulates atmospheric oxygen. So it's not free to regulate CO2 at the same time. So we think the CO2 concentration is regulated over long time scales by this cycle shown on this slide. If we start on the left, CO2 dissolves in rainwater to give you carbonic acid, and that falls on the land surface and weathers silicate rocks, represented here by the mineral calcium silicate, which is actually the mineral wollastonite. Most silicates are more complicated than that, but this is representative of what happens. You dissolve the calcium and magnesium silicates, releasing calcium ions, bicarbonate ions, and dissolve silica. Those products of weathering collect in groundwater and streams and flow down to the ocean and rivers, where in the ocean, organisms that live in the surface ocean use the calcium and bicarbonate ions to form shells of calcium carbonate, releasing one CO2 molecule in the process. Then when the organisms die, they fall down into the deep ocean. Most of them redissolve because the deep ocean is slightly more acidic than the surface ocean, but some of them accumulate on the seafloor to form carbonate sediments. The seafloor, though, is not just sitting there. As we know, because of plate tectonics, the seafloor is spreading. At some plate margins, seafloor is subducted, carbonate sediments are carried down and undergo a process called carbonate metamorphism, whereby calcium and magnesium carbonates recombine with silica, which by this time is the mineral quartz, to reform calcium and magnesium silicates and release gaseous CO2 in the process. And then that CO2 comes out through volcanoes at these arc systems. So let's think of that. That process is slow compared to the organic carbon cycle, but on a geologic time scale, it's actually pretty fast. It's fast enough to recycle all the CO2 in the combined atmosphere-ocean system on a time scale of about 500,000 years. So on the time scale of Earth history, the billions of years of Earth history, this cycle is more or less instantaneous. So think about what happens on the early Earth. I didn't mention the faint young sun problem yet. I mentioned that stars get brighter as they age. If you look at our own sun, that means as you go back in time, the sun was dimmer. We think it was about 30% dimmer 4.6 billion years ago, and then it's brightened more or less linearly since then. All other things being equal, if you had the same CO2 content in the atmosphere as you have today, the Earth would have frozen over completely prior to 2 billion years ago. But think about what happens if the Earth freezes over. The oceans would freeze, and this carbonate silicate cycle would virtually draw to a halt, because silicate weathering requires liquid water to go at any appreciable rate. On the other hand, carbonate sediments would still be dragged down in subduction zones, and so volcanism would continue. In fact, there's other forms of volcanism too. There's point volcanism, like you see in Hawaii or Mount Etna, and there's volcanism at the mid-ocean ridges. So CO2 is always being outgassed. It would build up in the atmosphere because weathering would be slowed. And finally, you would build up enough CO2 to melt the ice and reestablish liquid water. So we think that most of Earth history, it doesn't go that far. You don't globally glaciate, but silicate weathering slows down as CO2 builds up or as the climate cools. And so CO2 acts as a negative feedback on that cycle, on climate. All right, well, if you buy that argument, then you can use that to estimate a width for the habitable zone. Here's a diagram which is based on some old calculations that I did way back in 1993. It's not my diagram. You can see that it was made by some Europeans, because 0,1 is 0.1. This x-axis is the radius of the orbit in astronomical units, so relative to the Earth's orbit, and the vertical axis is the mass of the star relative to the sun. as I said, this is an old slide back when there were still 9 planets in the solar system. I've X'd out Pluto because Pluto has been deplanetized because there are objects out in the Kuiper belt that are bigger than Pluto. Anyway, the blue strip here is the habitable zone, is calculated from my 1993 model. Notice that the title says the ZAMS habitable zone. ZAMS stands for zero age main sequence. Because stars brighten as they age, if you make a diagram like this, you have to pick an age in the lifetime of each star. So this is what the habitable zone might have looked like when the sun first entered the main sequence, or when any of these stars enters the main sequence. At that time, Earth is the third rock from the sun here. At that time, Earth was sort of in the middle of the habitable zone, according to our calculations. Venus was inside it already, and Mars was just outside of it. Although I'll show you in a moment that early Mars actually looks as if it was habitable. Okay, so how do you calculate those boundaries? As I was saying, I'm not going to go into detail, but that's the part of the problem that my students and I have worked on over the years. On the inner edge, we build one-dimensional climate models. They're technically called radiative convective models. And our models predicted, at least at that time, that the inner edge you would develop a runaway greenhouse at something like 0.95 astronomical units, which coincidentally is right where Michael Hart had it. So actually the inner edge hasn't moved much since his original calculations. The outer edge, though, is very much different because of the feedback from the carbonate silicate cycle. We assume, imagine that if you push the Earth farther away from the sun, it should get colder, and then the carbonate silicate cycle feedback ought to cause CO2 to build up. So Hart's outer edge was at 1.01 AU. Our outer edge is way out at 1.67 AU, which is well beyond the orbit of Mars today. Mars is at 1.52 AU. And there's some point, though, at which that logic fails because the CO2 starts to condense out of the atmosphere. And we call that the maximum greenhouse limit. There are always skeptics out there that don't believe climate modelers. This is true on the modern Earth, where some skeptics don't believe in global warming and these very complicated 3D climate models. There are even more skeptics about one-dimensional climate models. So to counter that, we also define empirical limits on the habitable zone. If you look at Venus in the visible, you can't see the surface because it has these reflective sulfuric acid clouds. But if you look at radar wavelengths, as the Magellan spacecraft did many years ago, you can see the surface, and there's no evidence of flowing water or plate tectonics for that matter. We think that the surface, based on crater ages, is about 1 billion years old. So there's empirical evidence that Venus hasn't had liquid water for the last 1 billion years. So we call that the recent Venus limit. Mars, on the other hand, if you look at it, which we've done many times now from spacecraft, is covered, the southern highlands are covered with fluvial features. There was clearly liquid water running on the surface. There may have been seas or oceans. And so despite being a little bit outside our theoretical habitable zone, it looks like early Mars was habitable. So that gives you an empirical limit on the outer edge of the habitable zone. So if you put all that together, we now draw our habitable zones more like this. So this drawing is done on different scales here. The x-axis, instead of being distance from the star, it's the amount of sunlight or starlight hitting the planet relative to that on Earth. So here at 100%, there's the Earth up there. Here's the sun, this yellow star here. The vertical axis is now stellar effective radiating temperature instead of stellar mass. The sun, as many of you are astronomers. So the sun is a G2 star. It has an effective radiating temperature of about 5780 kelvins here. So the reason that we've rescaled things here is that this expands the habitable zone. Instead of being a narrow strip running through physical space, the habitable zone is roughly the same width on around in these units around different types of stars, right? And here are the theoretical limits that I mentioned. The yellow curve is the runaway greenhouse limit. The blue curve is the maximum greenhouse limit. This orange one out here is the early Mars empirical limit. And the red one in here is the recent Venus empirical limit. These objects down here at the bottom are objects that were discovered by the Kepler Space Telescope. And don't pay too much attention to them because this version of the slide is several years old. And I'll show you a more up-to-date one that has more planets and ones that were on it, ones that we're pretty sure are rocky. So we use this nomenclature and we now define the theoretical limits. We like to call that the conservative habitable zone. And, you know, we've argued in papers that if you're designing big space telescopes, which I will talk about in the last part of this talk, you should be conservative in your estimates. And sure enough, these people designing space telescopes are using the conservative habitable zone to get their estimated planet yields. On the other hand, if you're more optimistic, maybe after these telescopes get built, you might want to look in this broader region here, so that we call between the empirical limits, so we call that the optimistic habitable zone. Just 2 weeks ago, a paper came out in Nature that adds another wrinkle to this. Maybe some of you have seen this. This was a paper by Martin Turbay and colleagues. Turbay works with Francois Forget, or he was a student with Francois Forget over at the laboratory, LMD laboratory, Laboratory de Meteorologie Dynamique over in Paris. And their paper was on Venus, really, not on the habitable zone, but they argued in this paper that if Venus started out with a steam atmosphere, that atmosphere would never have condensed. And that counters some earlier calculations by Michael Way and colleagues, where if you've read any of Michael Way's papers, he's a planetary science from NASA Goddard. They've been arguing that Venus might have had liquid water for several billions of years. And in Way's model, clouds cool the planet, but in the new Turbay model, which starts with a steam atmosphere, clouds actually warm the planet. And they show that planets are even less stable towards the inner edge than what we thought. So here's another version of the habitable zone, which my student Sonny Harmon and I wrote a News and Views piece for this Turbay article. The Nature editors pushed the sun over here on the other side. So the sun has now moved over to the right of the diagram, but this is a habitable zone diagram, again, in terms of the amount of sunlight relative to Earth today. It has those limits that I just showed you. Let's just look here at the theoretical limits. That's these yellowish bars here. Here's the conservative habitable zone that I just described. On Martin Turbay's model, if the Earth had formed inside, or if the Earth had formed with more than 92% of the present solar luminosity, it would have developed a steam atmosphere and water would never have condensed. So these moving planets down here, this is what actually happens physically is that the habitable zone moves out with time as the star brightens. But if you plot things on this scale, then the planets appear to move inward with time. So you can see that the Earth formed out here at 70% solar luminosity because the sun was 30% less bright when it formed. The Earth has migrated in towards the runaway greenhouse limit here. And it's actually inside the Turbay threshold, but when it started, the Earth probably had a steam atmosphere as well. It was, the sun was dim enough at that time to allow the oceans to form. So anyway, there's a new limit on this habitable zone diagram shown in red here from that Turbay paper, and we call this region in here the pessimistic habitable zone, because planets that formed outside of that may never condense a liquid ocean. Okay, so that's enough on habitable zones. I'll show you one more slide towards the end with some up-to-date planets on it. So let me just quickly give you a few recent developments in the search for habitable planets. Let me talk briefly about the Kepler mission. It's not really so recent because this mission operated from 2009 to 2013. Some of you probably, all the astronomers are probably aware of it. Kepler was about a one meter telescope up there. That's smaller than the Hubble. The Hubble is 2.4 meters, but it was capable of monitoring the brightness of 160,000 stars very accurately enough to detect the transit of an Earth. So here's the Kepler field of view. It just for 4 years, it stared at this patch of sky right off the plane of the Milky Way, where you get a high star density, but you're not obscured by the dust clouds that are in the plane of the Milky Way. And Kepler could measure the brightness of a star to 1 part in 10 to the 5th and do that simultaneously for 160,000 stars. So it was really quite a technical achievement. What did we learn from Kepler? Well, we learned what is the value of eta sub Earth. Eta sub Earth is a term that the astronomers use. It's the fraction of stars that have at least one rocky planet in their habitable zone. More people are familiar with the Drake equation, which Carl Sagan and Frank Drake used to use to estimate the probability of intelligent life. Eta sub Earth is like N sub E, the third term in the Drake equation. N sub E was the number of Earth-like planets per planetary system. Eta sub Earth is just N sub E could be greater than 1. Eta sub Earth is like that, but it's a fraction between 0 and 1. And what Kepler taught us from statistics is that eta sub Earth is probably at least 0.2 for M stars. Their data are better for M stars because the planets are closer in. They're bigger relative to the stars, so you get a better transit signal. You also get more transits because the orbital periods are shorter. So we've known for 5 or 6 years that eta sub Earth, we've had a pretty good number for M stars. More recently, there was a paper published just earlier this year by Bryson et al. And they estimate that eta sub Earth is about 0.5 for G and K stars. Remember that the sun is a G star, K stars are a little dimmer in between G stars and M stars. So the statistics there are not very good, but the results are very exciting to those of us who are interested in searching for life, because it looks like there is a good possibility of finding rocky planets in habitable zones. What else have we learned from Kepler? Well, we've learned that big planets are not rocky. So if you have, Kepler gives you the size of the planet relative to the star. So if you can estimate the size of the star from models, then you can also estimate the size of the planet that transits it. Some of the Kepler objects are near enough that you can also measure their masses using the radial velocity method, which I'm not going to talk about, but that's the Doppler method. The star is pulling on the planet, but the planet's pulling on the star. So the radial velocity method gives you m sine I, where I is the inclination of the orbit. But if the planet transits, you know that the inclination is 90 degrees. So you get the true mass of the planet. If you know its mass and radius, you can calculate its density. So here's a rather old plot from 7 years ago showing densities of some of these Kepler targets. Earth is about 5.5 grams per cubic centimeter. So Earth is somewhere right around here on this graph. And you can see from this old kind of scratchy data that there seems to be a peak in density at maybe 1.5 Earth radii, and then it falls off above that, probably because these planets are capturing gaseous envelopes, like they're turning into gas or ice giants. Here's a slightly more up-to-date figure from Fulton et al. 4 years ago. And the data by this time were better, that you can now start to see a radius gap here between about 1.6 and 2 Earth radii. We think that the planets on the lower side of this are probably rocky planets here. The planets on the upper side of this are mini Neptunes, they're called. Neptune is about 4 Earth radii. So these are smaller than Neptune, but they're still probably gas or ice giants. And so not good candidates for Earth, for life rather. Another development which was mentioned in Adriana's talk this morning, or in the question and answer session, is we know there's a planet orbiting around Proxima Centauri. Proxima Centauri is an M star. It's part of the Alpha Centauri triple star system. Proxima is the closest star to the sun. It's only about 4 light years away. The planet does not transit its star, but it was found by the radial velocity method by the HARPS group using at the European Southern Observatory in Chile. M sin I is 1.27, so it's a little bit more massive than Earth, but it's almost certainly a rocky planet. And then finally, another system that was mentioned in the talk this morning is the Trappist-1 system. This is a system of 7 or 8 very coplanar planets, all orbiting a very late M star. Trappist-1 has a mass only 8/100ths that of the sun, so it's just barely able to burn hydrogen, and its planets are all very close. But as this figure from the original paper by Guion et al. Showed, that 3 or 4 of those planets are within the habitable zone. So one more habitable zone slide here. Updating that figure I showed you earlier, here's the conservative habitable zone and the optimistic habitable zone. Down here is Proxima Centauri b, which is nicely centered in the conservative habitable zone. And I'll show you in a moment that may be observable from the ground, actually. And here's at the very bottom, this is the Trappist-1 system. So 3 of the planets, E, F, and G, are within the conservative habitable zone, and Trappist-1b is in the optimistic habitable zone. So those are all targets for future space or telescopic observations. I should say that all of these planets now have masses less than 1.6 Earth radii. So we think that they're still mostly Kepler objects, but they're rocky planets, not gas giants. All right, so that brings me to the last part of the talk, which, as I said, it's short, but it's the most exciting part. How can we observe potentially habitable planets in the future? In the US, we've been waiting for the James Webb Space Telescope to launch. We've been waiting about 8 or 10 years. It was supposed to launch a long time ago now. It's now supposed to launch in December. That hopefully will be very exciting. JWST is a big telescope, 6.5 meters, which is about 3 times the diameter of the Hubble mirror. It's a segmented mirror. It operates in the near infrared, basically. So it's not quite a duplicate of the Hubble, but that may be able to get spectra of transiting planets. It can only do transit spectroscopy. It doesn't have a good enough coronagraph to look for planets that don't transit their star. But JWST will be used to look at the Trappist-1 system and study those planets to see if any of them show signs of habitability. Here's an artist's conception of the extremely large telescope that is being built now, I understand, at the European Southern Observatory. This thing is going to be 39 meters in aperture, which is huge. The biggest ground-based telescopes right now are the two Keck telescopes in Hawaii, both of which are 10 meters in diameter. So this will have almost 4 times the diameter and 16 times the collecting power, light collecting power. One can, with this telescope, Ignace Snellen has shown that one can actually look at nearby planets, nearby being meaning the Proxima Centauri B in this case. This telescope is big enough to separate Proxima Centauri B from its star. You know, it can beat the diffraction limit there, and it can hopefully get a spectrum of that planet's atmosphere. So as Snellen has shown, if that planet had oxygen in its atmosphere, you should be able to detect it because you're getting enough photons to resolve individual vibration rotation lines that are superimposed on the electronic spectrum of O2. That technique is called direct imaging because you're looking for reflected light from the planet rather than looking for a planet transiting the star. The best place to do direct imaging is up in space because then you're not obscured by the atmosphere. You can do it in either the visible or the thermal infrared. And NASA has thought for some time that it's easier to do this in the visible. So they've been studying 2 different direct imaging space telescopes. The top one here is called LUVOIR, which sounds French, but it isn't. That's NASA proposed telescopes, the large UV optical infrared space telescope. There's 2 versions of it. One is 8 meters in diameter and one is 15. Neither of these, of course, is approved. In fact, the US astronomers have completed their decadal survey, but they haven't released it yet. So we don't know if they've picked either of these telescopes for the next big flagship mission. HABEX, I should say LUVOIR, would separate out the light from the planet from the star using an internal coronagraph. HABEX, the Habitable Planets Explorer, is a smaller telescope, 4 meters in diameter, but it would probably have a star shade on it, which would allow it to do, even though it's smaller, it could still find a lot of exoplanets and do direct imaging on them. What would we be interested in seeing if we could get spectra of these habitable exoplanets? Well, we'd like to look for biosignatures, and I'll only mention what I consider to be the best biosignature, which would be the simultaneous presence of oxygen and methane. Most of the oxygen in Earth's atmosphere is produced by photosynthesis. Most of the methane is produced by methanogenesis. So these gases are 20 orders of magnitude out of thermodynamic equilibrium. And if you could see both of them at the same time, you'd be pretty convinced that I would be pretty convinced that there was life on the planet. You can look for these things in the spectrum of the Earth. So here's a spectrum that back 20 years ago, I worked with NASA on another direct imaging space telescope called Terrestrial Planet Finder. At the time, we were puzzled about how to get a single pixel resolution spectrum of the Earth. Orbiting satellites are generally too close to do that. And NASA was thinking of spending $20 or $30 million to put a space telescope out at the L1 Lagrange point. But then some of my astronomical colleagues went out to Kitt Peak and used the telescope there to get an Earthshine spectrum of the Earth. What is that? Well, here's a picture of the moon. If the moon is in crescent phase, of course, you can see the bright side because of reflected light from the sun. But if you have a dark night, you can also see the dark side of the moon. And why is that? Well, that is because there's sunlight that comes from the sun, bounces off the Earth, hits the moon, and then is reflected back to the Earth. So that if you take a spectrum of the dark side of the moon and subtract a spectrum of the bright side, you get rid of the lunar spectrum and you get a single pixel spectrum of the Earth. So that spectrum is shown here in this scale. This is the x-axis is angstroms, which is an angstrom is 1/10 of a nanometer. So the visible goes from 4,000 to 7,000 angstroms in this picture. And this vertical scale is a measure of flux or intensity. You can see, and then the black curve there are the data from the Earthshine data. The red curve down at the bottom is a model fit to that data. And I'll just point out that you can see interesting things. There's a very broad ozone band here in the visible. There are H2O bands in the near infrared. And right here at 7,600 angstroms or 760 nanometers is the O2A band, which is a forbidden electronic transition of oxygen, but it's actually very visible in the Earth spectrum. So all of these direct imaging space telescopes would be designed to be able to look for that in an exoplanet spectrum. All right, so that brings me to the end here. Let me leave you with 4 conclusions. First, 5 conclusions. First, that detectable life requires, at a minimum, a planet with a solid or liquid surface, a free energy gradient, availability of carbon, and surface liquid water. Habitable zones should be defined conservatively if they're being used to generate parameters for future space telescopes. Big 30 to 40 ground-based telescopes may be able to characterize some nearby M-star planets, maybe only Proxima Centauri b. JWST may be able to get transit spectra of an Earth-like planet around some M-stars like Trappist-1. And finally, my last point, in the long run, both NASA and ESA and myself want to do space-based direct imaging of exoplanets because that's our best chance for finding Earth-like planets and life. So I will quit there and open it up for questions. And I'm going to stop the share here so that people can see better.
Okay, thank you so much, Dean. It was really a very nice talk. Thank you. So we have some questions here at the Zoom. So Gustavo, do you have a question, please?
Hi, Jim. Thank you so much for this very nice talk. As someone who has been reading your paper for decades now, I ask you, what do you think would be the next great theoretical breakthrough to make the habitable models more realistic? What's the next big avenue of theoretical exploration?
So what needs to be done to make the models better is to go to 3 dimensions. And I mentioned one 3-dimensional model, the Turbay model that was just published. In fact, I guess I forgot to say that was a 3D climate calculation. You need three dimensions to do clouds. There was another calculation that I didn't mention from that same group. This was Jeremy Leconte and colleagues in 2013, also using the French LMD model. And although I didn't mention it, they did a calculation of the inner edge of the habitable zone, which was much better than ours. So we've adjusted our 1D results to fit their 3D models, right? So people can easily improve on our old 1D calculations but it takes a lot, more work because these 3D models are more difficult and time consuming.
Thank you. Would you say that clouds still remain the big problem in this calculation?
Yes, and if you read our News and Views article on the piece on the Turbay article, it's all about clouds, right? So Michael Way in their model, that was a 3D model also. In their model, clouds cool early Venus, and in the Turbay model, clouds warm early Venus. The difference in that case is a matter of initial conditions, because Mike Way assumed that there was an ocean already present on the surface, whereas Turbay assumes you start with the ocean up in the atmosphere as steam. But it's groups like that will be pushing the envelope on these calculations in the future.
Thank you.
Okay, thank you, Gustavo. I think, Renato, do you have a question?
No, I clicked by mistake. Well, since you gave me the word, I can ask if there is any special GTO program for GWST that I think they're quite several. They're very specific about particular planets already, right?
Oh, they are. You know, I'm not an observational astronomer, so I don't apply for telescope time, but they've already, I think, allocated all the time on the first observation cycle for JW. And in fact, you know, I don't know how far down they've scheduled it. I do understand that the Trappist-1 system, a couple of those planets are high on the target list. So I'm really looking forward to seeing those things observed.
Okay, thanks. Very great talk, by the way.
Okay, thank you, Renato. Luis Felipe, do you have a question?
Yes, I do. First, thank you for this great lecture. I would like to make a question. We already know some potentially rock exoplanets inside the habitable zone of their stars. And you talked about some cases like Proxima Centauri b and the Trappist-1 planets. But which ones you believe that have greater chance of having liquid water in their surface and possibly life?
Okay, so now I'll give you the bad news. I think Proxima Centauri b and the Trappist-1 system, I think all those planets are actually not inhabitable. And why is it? It's because they're orbiting M stars. And I didn't have time to go into the problems with M stars, but you heard some of them in Adriana's talk this morning. They're very magnetically active. They have lots of flares, strong stellar winds. So that can strip a planet of its atmosphere. There's another problem with M stars that's even worse that she didn't mention, and that's that they have a long, slow contraction phase when they're forming. So, you know, the sun, if you think about the pre-main sequence evolution of the sun, we think that the sun was initially about 3 times brighter than when it hit the main sequence during this contraction phase. But the sun forms on a time scale of, 2 or 3 million years or even less. With an M star, the formation time scale can be up to 1 billion years for a late M star like Trappist-1. And because the main sequence luminosity is so low, the luminosity in the contraction phase can be 10 or 20 times higher than the luminosity when it hits the main sequence. So these planets that look like they're in the habitable zone of their star, or, you know, Proxima Centauri b or Trappist-1, we're actually getting irradiated by, you know, many times the runaway greenhouse limit of stellar flux during the time. I mean, the planets form quickly because they're close in, the star forms slowly, and so I think they're all completely devolatilized, my prediction.
But we have some planets, some rock exoplanets inside the habitable zones around K stars, don't we?
There are planets that are from the Kepler set around K stars, right? But most of those Kepler objects are far away, right? So to get spectra, the other thing I didn't say, transit spectra of rocky planets are really scrappy. So JWST is going to get transit spectra of the Trappist-1 planets, but even if you had an Earth analog planet going around Trappist-1, I asked one of my recent graduate students was Natasha Batalha. Her mother, Natalie, was Kepler chief scientist for a while. We asked Natasha, what would you be able to see spectroscopically on an Earth analog going around Trappist-1? And she drew a straight line on the blackboard with a little dip at 2.2 microns. The only thing that JW could see would be the 2.2 micron band of CO2. It couldn't see oxygen or anything else in the water, anything else. So that's why I emphasize the direct imaging space telescopes in my talk. I think we really need to wait until we get those telescopes built, and they're actually optimized for FGK stars. So, and you know, as I just said, FGK stars are actually much better candidates for hosting habitable planets. So we need to get Habex or LUVAR up there.
Okay, thank you very much.
Okay, thanks, Luis. I think Matthias, do you have a question?
Yes, I have. Hi, Dr. Kasting. Thank you very much for your talk. I am a big fan of your work. Yeah, recently I was working with your model, and I have the next question. You fix the amount of water in the model, in the climate model. And my question is, what was the difference, or what will be the difference if each planet has different amount of water? What will the difference in the, I don't know, in the greenhouse effect or in the profile temperature pressure that are inside the model?
Yeah, so that's a good question, and it goes back to what we talked about earlier, the difference between 1D models and 3D models. In our 1D models, you know, in a 1D model, you can't really do clouds self-consistently. So we stick clouds at the ground and just use them as part of the surface albedo. You also can't predict relative humidity in the atmosphere. So we assume a saturated troposphere. We know that's too much water in the troposphere, but we really don't know how to do better than that in 1D. If you go to a 3D model, then you've got a hydrologic cycle in the model. You can try to predict the clouds, although they're still difficult. You can predict the water vapor much better, so you can predict the relative humidity distribution semi-realistically in a 3D model. And you've got 3 dimensions, so you could then cover as much of the surface with oceans as you want, right? So you could do this experiment that I think you have in mind, where you put different amounts of water on the planet. So you need to use 3D models to do that.
Okay, thank
you. Okay, thank you, Matthias. Jean, I have a question. You said at the beginning of your presentation about the Carl Sagan movies, Cosmos, with the possibility of life in giant planets or something like that, in the atmospheres of giant planets. So, okay, Venus is not a giant planet, but what do you think about the possible detection of phosphine in Venus?
Oh, well, you know, I, like a lot of other people, I got real excited about that when it was announced, when about 2 years ago, no, just 1 year ago now, it was fall of 2020. And you know, there are people who have been proposing for some time that there could be life in the Venus clouds. And part of that, you know, that's the reason why this new Turbay paper is actually meaningful, because in order for you couldn't start life in the Venus clouds. It's not a stable pressure temperature environment. But if you had liquid water on the surface, you could conceivably have originated life on Venus surface, and then as the surface got too hot, it organisms could have taken refuge in the clouds, right? So that idea has been out there, and then Jane Greaves and colleagues came along and claimed to measure phosphine in the microwave. But you know, so I got real excited, started trying to figure out if there was an abiotic way to make phosphine, but pretty shortly after that, some of the other observational astronomers weighed in, including Ignace Snellen. You may know he wrote a paper in 2020 really debunking the Greaves et al. Claim and showing that that was almost certainly an artifact. I know Ignace pretty well because he was my host. He invited me over to Leiden to give some talks 2 or 3 years ago, I guess it was. And he's a very sharp guy, and I think he's right about this. So phosphine is dead for the moment.
Okay, thank you. So let's see if you have questions at the YouTube. Raquel, Vinicius.
Hello, James. I'm pulling up the question here. First of all, great talk. I mean, it's definitely one of the most talked about topics in astrophysics when you talk about habitable zones and life outside Earth. And it definitely brings a lot of people to talk about it. So from YouTube, we have a question. It comes from Diogo Souto, and they ask about the Earth spectrum. And he wants to know if we can see methane on that spectrum.
Yeah, okay, I should have mentioned you can't see methane on that spectrum. It's not a high enough resolution spectrum to do that. And methane is also not very abundant in Earth's atmosphere. It's only 1.6 or 1.7 parts per million. Now you could see methane if you had a bigger telescope. So if you get more photons, you can, you get a better spectrum, then you could see methane. I don't think that even, I may be wrong about this, but even the big version of LUVAR, the 15 meter, I don't think that could see methane in Earth's present atmosphere. But the way I see it, that's not a fatal problem, because if you, let's say that you build any one of these big space telescopes and you see a nearby exoplanet that has O2 in its atmosphere, which all of these telescopes could see, I think that would get everybody really excited, and we would build some other telescopes. I think it's easier to see methane in the thermal infrared, actually. So there's another version of direct imaging telescopes where you use an array of infrared telescopes, like the Darwin array that the Europeans worked on for many years. So there's ways to follow up on these missions and answer that question.
Great, thank you very much.
Hi, James. First of all, thank you so much for the lecture. It was amazing. And we have another question from YouTube made by Pedro Henrique Nogueira, and he's asking, do you or others in the field also consider tidal heating on habitable zones modeling?
Yeah, well, I haven't done it myself, but Rory Barnes at University of Washington in Seattle has written papers on that. And so he's got habitable zones that are modified by tidal heating. And of course, tides, that makes a big difference on Enceladus and Europa, right? So though I'm not sure it will, well, I'm not sure it's not that easy to keep surface water on with tides. You can keep subsurface, you can definitely generate subsurface water. I don't think that necessarily helps you much though with exoplanets, unless somehow subsurface life could produce well, I'm thinking back, I haven't read Rory's paper. I think he must be focused on surface water. So he's focused on extreme tidal heating, and yes, there's ways to expand the habitable zone. I should say that there's other ways to expand it. Sarah Seeger wrote a paper, a piece in Science about 10 years ago, showing that if you have a rocky planet with a dense hydrogen atmosphere, H2, hydrogen is a surprisingly good greenhouse gas if you have a lot of it. And so she actually had a picture in her piece showing the habitable zone going out to 10 astronomical units, Saturn's orbit, for I think it was a 3 Earth mass super Earth with a 30 bar captured H2 atmosphere. So, if these things exist, they could be habitable.
Thank you.
Marcelo, I have one more question, if possible. You're muted.
You're muted, Marcelo.
Sorry. I think there are the two questions at the YouTube. I don't know if the students, you made the questions. Okay.
Yeah, we have two more questions.
Okay.
That's fine.
Okay. The first one is from J. Silva Cabrera. Great talk. Is there a characteristic albedo value for rocky planets? And could a nice surface planet from direct observation be confused with a giant planet?
Well, we know that the Earth's bond albedo is about 0.3. And, I don't know that that's necessarily characteristic. Mars albedo is about 0.2. Venus's albedo, of course, is 0.8 because it's got the cloud layer. Actually, here's something that most people don't know. If you take away the sulfuric acid clouds on Venus, what would its albedo be? That's something we can do with our model, and its albedo would still be 0.6 because if you have 90 bars of CO2, CO2 is a really good Rayleigh scatterer. And so you reflect sunlight with Rayleigh scattering. So back to your question, you don't know the albedo of a planet to begin with. I think the way to distinguish a rocky planet from a giant planet is, the better way to do it is if you can get their masses. Right. We used to talk about this back in the old TPFC days. I told you NASA was started on one of these telescopes about 20 years ago and then quit. And some people would argue that you could make assumptions about the albedo, and then other people would say, no, you really can't make assumptions about the albedo. So I think you need data. You can get masses, you can do it either by radial velocity in some cases, or there's another type of space telescope which has been talked about to do astrometry rather. And back 20 years ago when we were working on TPFC, NASA was also working on a telescope called SIM, the Space Interferometry Mission. And astrometry, you're measuring very accurately the position of the star in the sky. So you can see the planet pulling the star back and forth and up and down in the plane of the sky. And that's actually potentially more accurate than radial velocity if you do it from space. So that, I think the real way to answer your question is to build something like that and measure the mass of the planet.
Okay, thanks.
On to the last question from YouTube. This one comes from Diogo Souto again, and they ask, what if there is a catastrophic nuclear event on Earth or any other planet? Would we be able to see such a signature on the exoplanet atmosphere?
I haven't thought about that one. The Earth would become, you could get a lot of smoke and fires. You could get a planet that was enshrouded in smoke, but I don't know. Think about the possibilities. If you had something like that, you have a nuclear war, the aftermath would last for days or weeks or something like that, the observable aftermath. Whereas, the solar system's been around for 4.6 billion years. So what are your chances of catching a planet at that particular point in time? I think statistically, it's just not going to happen. And I would hope it wouldn't happen. That'd be a terrible time to see a planet.
Okay, thank you, Vinicius. I think, Gustavo, you have a question?
Yes, just a short one. First, I have to make sure that I got the numbers right. You mentioned that the total time scale for recycling carbon from the carbonate silicate is 500 million years, 500 million years.
No, half a million.
500 million years. That's why you mentioned that it's actually
much faster. Right. So it's very fast compared to the solar evolution time scale.
Are you thinking about recycling all of the carbon dioxide in the atmosphere?
So actually that time scale is to recycle all of the carbon dioxide in the atmosphere plus oceans. There's about 60 times more CO2. Most of it is dissolved inorganic carbon in the oceans. So if you take that total reservoir and divide by, say, the volcanic input rate, you get 500,000 years. See, I mentioned the organic carbon cycle. That is fast. That's recycling all the atmospheric CO2 on a time scale of about 10 or 12 years. So, you know, it's really ripping around, but that's still not what controls the CO2 level on long time scales.
But that does not apply to the sequestered carbon in solid form, say in carbonate. There's about 100 bar of carbon in solidified form. This time scale does not apply to the solid carbon.
There's not that much soil carbon. So the numbers that I've seen, there's about 2 or 3 times as much carbon in the soil as there is in the atmosphere. Okay. So living plants plus soil is maybe 3 times the atmosphere. And just, you know, on a different subject, that's why we're not really likely to solve the global warming problem by growing trees, because there's not enough place to put it. And CO2 may come out of the soil as the climate warms.
Okay, thank you.
We have a question from YouTube.
Okay, so this is the last one? Okay.
I believe so. It was the question was made by Ricardo Oliveira, and it is wouldn't spectrography detect the signature of radioactive elements contained in the atmosphere?
No, you can't see radioactivity. So that's releasing particles, alpha and beta particles, basically electrons and helium nuclei. So you're not seeing that. You're only seeing electromagnetic emissions. I guess there might be some neutrinos coming out and maybe even some high energy photons. But, you know, think about the photon problem. Here's something an interesting factoid back when we worked on TPFC. You know, that was an 8 by 3.5 meter elliptical telescope. And if you looked at an Earth-like planet 10 parsecs from here, or about 30 light years, you could count the photons coming in from that as they arrived. You could count them by hand. They're coming in that slowly, right? So that's in the visible, where, you know, the star's flux maximizes. So getting to other parts of the electromagnetic spectrum is almost impossible for an exoplanet.
Okay, thanks.
Okay, so thank you, Raquel. So I think this was the last question. So I would like to say thank you so much again, Dr. Kasting, for this excellent talk. And I would like to invite everybody to come back tomorrow for the second day of the Astrobio Online. Okay, thank you so much.
Okay, thanks. And I hope I get to